All right. uh, Good afternoon, class. Mr. P back again. Um, I'm pretty excited. My forge arrived from Lithuania today, so I'm still waiting for a bunch of other items to arrive. But my forge is all my tools for my forge are coming together. It's exciting. So I'm hoping in the next couple weeks I'll be able to get some metal really hot. Should be fun. um, all right, so I've got. I actually just got the forge like 10 minutes ago, so I haven't opened it yet because I told you I'll post a picture of it or I'll show it tomorrow. Um, so all right, so I've got two questions that we're going to do today from this paper 2. This is the May 2018 Time Zone 1, paper 2, and I'm going to be doing questions 4 and 6. So, that's question 6. That's question 3. Question 4. All right. I think this will be a pretty quick lesson today because it's just 2 questions. So we're doing question 4. An ohmic conductor is connected to an ideal ammeter and to a power supply of output voltage V. The following data are available for the conductor. Okay. The ammeter reading is 2 amps. Calculate the resistance of the conductor. Okay, so the resistance of the conductor, we learned an equation for resistance. It was rho L over A, where rho is the resistivity. So the resistivity, it says, is 1.7 times 10 to the negative 8 ohm meters. The length, we can see that it is a 0.02 times 0.02 times 10 centimeter. So it looks like the length is 10 centimeters. So that's 10 times 10 to the minus 2 meters. And then the area, it's clearly a rectangular cross-section, or a square cross-section. So it's 0.02 times 10 to the minus 2, because it's in centimeters, squared. And so we work that out. That'll be our resistance. 1.7 times 10 to the minus 8 times 10 times 10 times 2 divided by and that gives us a resistance of 0.043 ohms. Alrighty. B. Calculate the drift speed of the electrons in the conductor in centimeters per second. State your answer to an appropriate number of significant figures. So I taught you an equation for current, and I said that IB likes this equation, and it's talking about current at the microscopic level, and the equation is current equals Q N A V. QNAV, where Q is the charge of the charge carriers, which in this case they're electrons, N is the density, the number of charge carriers per volume. A is the cross-sectional area of the conductor that the charge is going through, and then V is their so-called drift speed. So we're told that the ammeter is reading 2 amps. So my current is 2. The charge is electrons, 1.6 times 10 to the minus 19. The density of electrons is 8.5 times 10 to the 22 per cubic centimeter. Okay. The area of the conductor is 0.02 by 0.02. Now, notice how the density of electrons is given in per cubic centimeter, and the dimensions are also given in centimeters. So if I just keep everything in centimeters, then I'm going to get the velocity in centimeters per second as opposed to meters per second. So I actually don't even have to worry about the fact that it's centimeters for this problem, times the velocity. So we can solve for the velocity. 2 divided by 19 divided by 8.5 divided by 10 to the 22 divided by 0.02 squared. Just double check that I typed that in correctly. Yeah, and so I got that the drift speed is 0.37 centimeters per second. Notice how it says an appropriate number of significant figures. And so basically, if you notice, none of the information is given to us with more than 2 significant digits. So I shouldn't give my answer with more than 2 significant digits. Okay. All right. Oh, that was it. That was nice and easy. Cool. So the next question I'm going to do for you guys is question 6. Question 6 says the radioactive nuclide beryllium-10 undergoes beta minus decay to form a stable boron nuclide. Identify the missing information in this decay. So let me write it out. Beryllium goes to boron plus, it says it's a beta minus, plus an anti-electron neutrino. So our beta, it's a beta minus that has a charge of -1, and it has a nuclide number of 0. The anti-neutrino has no charge, and it's not a nucleon, so its numbers are 0, 0. So one of the things we learned about radioactive decay is we learned that the charge has to be conserved, which is the bottom row of numbers, and then the nucleon number has to be conserved, which is the top row of numbers. So we can see in the top row, we have 10 equals an unknown plus 0 plus 0. So that means that the unknown has to be 10. And then for the bottom row, we have 5 minus 1 plus 0 equals 4. So we have to have 4 on the other side. Okay? So that's part A, just balancing the nuclear reaction. The initial number of nuclei in a pure sample of beryllium-10 is N0. The graph shows how the remaining beryllium nuclei in the sample varies versus time. on the graph, sketch how the number of boron nuclei in the sample varies versus time. Well, we can see that beryllium becomes boron. So the total number of atoms has to remain, or the total number of nuclei has to remain at n naught. But the beryllium-10 is going down and the boron is going up. So their sum has to add to the initial number. So the number of beryllium plus the number of boron has to equal the original number of nuclei. So that means that the number of boron equals n naught minus the number of beryllium. So basically we're flipping the graph upside down, and we're going to draw something that looks kind of like this. So we start out with no boron. When there is half of the beryllium remaining, that means we're going to have the same number of boron. When there is 75% beryllium, we're going to have 25% boron. When there's 25% beryllium, we're going to have 75% boron. So we're going to kind of just connect these curves into something that looks like this, like that. That's supposed to be curved, but something like that. Part 2 says after 4.3 times 10 to the 6 years, the number of produced boron nuclei divided by the number of remaining beryllium nuclei is 7. Show that the half-life of beryllium is 1.4 times 10 to the 6th years. Okay, so what that means is that the number of beryllium, there's 7 times as many boron as there are beryllium. So basically that means that 7/8 of the sample is boron and 1/8 is beryllium. Okay? Because that would give their ratio as 7. Okay? And then they add to just 1. So if we look at 1/8, 1/8 is equal to 1 over 2 to the 3rd. So basically what they're saying is 4.3 times 10 to the 6th is actually 3 half-lives. Okay? So we take 4.3 times 10 to the 6th and we just divide it by 3 and we get 1.4 times 10 to the 6th years. I don't know why that question is worth 3 points. It seems really basic to me. Okay, part 3. Beryllium-10 is used to investigate ice samples from Antarctica. A sample of ice initially contains 7.6 times 10 to the 11th atoms of beryllium-10. State the number remaining of beryllium-10 nuclei in the sample after 2.8 times 10 to the 6th years. So 2.8 times 10 to the 6th, that is going to be twice that, so it's 2 half-lives. So basically, after 2 half-lives, that means we're going to divide the initial amount by 4, because that would be 2 squared. So the number remaining would be 1.9 times 10 to the 11th atoms. Part C. An ice sample is moved to a laboratory for analysis. The temperature of the ice sample is minus 20 degrees Celsius. State what is meant by thermal radiation. Thermal radiation is electromagnetic radiation emitted by an object due to its non-zero temperature. Anything that has a non-zero temperature is going to emit thermal radiation. Then it says, discuss how the frequency of the radiation emitted by the black body can be used to estimate the temperature of the body. We learned the Wien displacement law, which says that the temperature is 2.9 times 10 to the minus 3 meters Kelvin divided by the wavelength at which most of the radiation is emitted at. Okay. And then lambda, we have C equals lambda F, so we can actually write the law as 2.9 times 10 to the minus 3 times F over the speed of light. So we could use that. All right. Calculate part 3. I'm just going to turn the page. Part 3 says, calculate the peak wavelength in the intensity of the radiation emitted by the ice sample. So we're going to use the Wien displacement law. The peak wavelength is 2.9 times 10 to the minus 3 meters Kelvin divided by the temperature. Now, keep in mind, this is the temperature in Kelvin. So minus 20 degrees Celsius in Kelvin, that is going to be 253 Kelvin. So 2.9 times 10 to the minus 3 meters Kelvin divided by 253. That gives 1.1 times 10 to the minus 5 meters. Okay. Derive the units of intensity in terms of fundamental SI units. So intensity is power per area. Is this the last part? Yes, it's the last part. So the units of intensity are going to be watts per square meter. However, meter is a fundamental SI unit, but watt is not. So I have to take a watt and break it down into kilograms and meters and seconds. So a watt is a joule per second. Okay. Joule, remember, joule is force times displacement. Or I can think of joule as energy, so I have 1/2 mv squared. So a joule is a kilogram meter per second that quantity squared. All right, so I can see that the meters will cancel. And then the seconds, I have kilograms over seconds cubed. That would be the answer. Okay, so kilograms, meters, seconds, Kelvin, amps, those are the fundamental SI units. Okay, so that's it for today. I'm assigning you guys questions 2 and questions 5. So thank you to the one person who watched live, Sofa. If you're still there, it says I have 2 viewers right now, but who knows? And I'll talk to you tomorrow with the last paper 2. And then next week we'll do a little paper 3 practice, and that's it. So have a nice afternoon. Bye.